Okay, so we are starting the next lecture, which is going to conclude B-trees. As you may recall, last time where we left off was we were sort of talking in the middle of insert, or the idea of the insert procedure in a B-tree. And so we had a tree that looked like this, and I've kind of got some layered overhead slides here. So bear with me while I layer them. Here, and then this here. So that was the tree we started off with, was the tree like that. And so what we had done first was we tried to insert 7. And we said that, well, 7 should go where 6 is. So in a sense, we duplicate that pointer, and we have 2 pointers to 8 left. And that meant that we needed an index between them. And so when we had leaves 6 and 7, a reasonable index between them could be 6. And so we went ahead and did this and inserted that value. And so then we had inserted the index 6 and the leaf 7. And that was our procedure then at that point for having inserted that node. And that was then case 1 of 2. We had said that the insert procedure we had to deal with was as follows. When dealing with insert, we would find the location for the new leaf. Would insert the new leaf, and then once we inserted the new leaf, we would then insert index into parent, and then once we were done there, we had to check the parent. And we had written this last time too, and we had a couple cases, and we need to talk about a special case today too. Case 1 was no overflow, and we would stop when we had that case, and that was the situation we had here. There's no overflow, so we can stop. Now, the next thing we did then was we inserted 20, and 20 would go where 19 was, because it was going to be less than 26, greater than 13, greater than 18, but less than or equal to 20. So it would go right where 19 was, which means what we did was then we split 19. We had a new child between 18 and 20, and then we would insert 20 as that leaf, and we inserted 19 as the index between them, and that left us then, if I want to replace this stuff, with a new tree that looked like this. The old side stayed exactly the same, and we had this part like this. So we inserted here 20 as another node between the indices 18 and 20. And then between the two of them, we needed an index, and so 19 became the index. And so that's how that worked. And what we did then was we said, well, now there's an overflow there, and that led us to case 2, where we said here we have a overflow. And so if we had an overflow, we split node, the parent gained a child and index, and we would continue. In other words, we would check the parent. And so this is where we had left off with this slide last time. And so what we finished off this example here by saying, well, because I am splitting this node, I then have the node end up looking something like this, where that node splits and starts to look like this. And so that should have left 19 hanging out by itself, because the middle, if we have 5 indices, then the middle one will be left over. When we have 7 indices, the middle one will be left over. The middle node is always left over. And so then that middle node was then left to, since we have now this pointer has split into 2, we have now an extra child in the parent, where we had 1 child, we had 2. We now need an index between the old child and its new split version. and so 19 moves up to become that child. And so we would have that situation. And so that's what we meant. We would split the node, the parent gained an extra child and an extra index, and now we check the parent for overflow. And here the parent does not overflow. We're okay. And so we had a case 2 in this section, and then we moved up to check the parent and hit a case 1. And we could have multiple case 2s before we have a case 1. What we could do is have here a situation where we try to insert, say, 11. 11 is less than 26, less than 13, greater than 8. So if I'm going to try and insert 11, well, it's going to be that I'll have a second pointer greater than 8. And so what I could do in that case then is say, well, I've got now the same tree I had there. Start out with, this is what I'm starting out with again. This is exactly the same tree I just had the previous slide. I've just now changed the overlap of the slides a bit. And now that I've got this set up, well, when we insert that 11, it gets inserted as another child to the right of 8, the index 8. And so what we'll have is something next to 9 and then a new index between that node and the new one, which gives us this. A lot of shuffling. 11 gets inserted to the right of the index 8, just like 9 was. And 9 gets inserted as an index between them. And then now you notice we have now we check the parent after we've done the insertion of the leaf and the index. The parent overflows, so we split the parent. And when we split the parent, the middle index 8 is going to go up into here because when we split this child into 2, the parent will gain a child. The parent should also gain an index. And so the parent will gain the index 8. And so we end up with this situation here, where 6, 8, and 9 has split into 6 and 9, with 8 moving up into the parent. So that was case 2. 13 there being between 9 and 18. It may not be, that maybe is a little bit easier to see it if I do that. And now we check the parent, and like the last example, we have an overflow here as well, because that has 4 children, and you're only allowed to have 3 in an order 3B tree, which is what this is. And so we need to split this node as well. 8 will be a subtree root, 19 will be a subtree root, and 13 will move up to become another index inside the root, because when this splits into 2, the root will gain another child, and so then we have this situation here. We have 8 and 19 as children, 13 moves up, and then that is one large root node with 13 and 26 as indices, and a pointer to 8 to 19 and to 40, 46 as children. So there we have an example of a situation where we have now done a split on this level and a split on this level, and then now the root we check, and the root doesn't underflow, so we're okay there. And so we had a case 2, and then a case 1. And you may rightfully ask, well, what would happen if the root overflowed as well? And if the root were to overflow, we'd have a situation where we have, let's say we inserted something else, and we ended up ultimately with, this was our old root, 1326. And then let's say we had here 8, blah, 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 and 19, blah, 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 and 40, 46, blah, blah, blah. And then the rest of it I'm not going to draw. But let's say we had that node, and let's say for some reason then we had it split here, and this node became something like 40, 43, 46 instead. And so this would split, and the root then would look like this, where we'd have 13, 26, and 43, and we'd have 8, 19, 40, and 46. So again, I'm not drawing the entire rest of the tree, but let's say that was the situation we had, where this was our tree as the last slide looked, and then we said, well, let's say we did some, we inserted, let's say inserted into here somewhere a few times, and then one of these nodes eventually split, and some new node moved into that parent here, and so that would then produce a situation where this node gained a child and a parent. And so this being 43. And so then this would split. 43 would move up into the root. We'd have 40 and 46 here. And so now you see the root overflows in that case because we have four children. And so the question is, what do we do? And the answer is, well, all you need to worry about here is the root splitting. So you have this situation where the root would split. You'd have 13 here pointing to 8 and 19, which would, of course, point to the other stuff. And you'd have 43, which would point to 40 and 46, which would point to their own stuff. And then 26 moves up. Just like before. That's what we did in the other cases, too. Same thing here. The root splits. The middle index moves up. The only difference here is there's nowhere for the middle index to move up into, and there's nothing for these to be attached to. So what we need to do is create a root. That is, what happens when we split is, this is sort of a special case. When the root overflows, you will first split the root. You have a new node. The children are the halves of the old root. Index is old root middle index. And then that new node is, of course, the new root. So we split the root into two pieces, and then we'll create a new node. And the children of that, the two children, will be the halves of the old root split, and the index inside that root will be the index you sent up from the split. And that's what happened here then. We had split 13, 26, 43 into 13 and 43. 26 was just sort of floating there in midair, and we said create a new node that'll hold 26 and will point to 13 and 43. So the only special thing about the root overflowing is that, unlike the regular overflow case, since we can't say the parent gained a child index because there is no parent, we have to create one. So we create a parent that, in a sense, basically now points to the two halves and has one index. And that works, because if you have one index, you have two children, because there has to be a difference of one there. So essentially, this then is why the root has to be allowed to have a minimum of two children rather than a minimum of b plus 1 over 2 children. The reason being, in the other situations, you have a parent that already has many children, and now with your split, is gaining one more. Where in this case, there was no parent of the root. So there was no magical node up here to now say, well, I pointed to just the root, and now I point to more than just the root. There wasn't a parent. All the other cases, we had a parent that had, say, b plus 1 over 2 children already, and now it gains one. Whether in the case of the root, there was no parent. And so since there was no parent to also be pointing to a bunch of other nodes. When we create this new node, the only thing it can point to is 13 and 43, the two halves of the split. There were no other nodes anywhere else for that to point to. And so there's no way the root could conceivably, out of the blue, go from not even existing to suddenly having b plus 1 over 2 children. It just couldn't work that way. And so the root being the top of the tree in sort of a special case, we have the new root be a special case, and we say, okay, the new root can point to as few as 2 children. We understand there'll be times when the root will need to point to as few as 2 children, and it won't have the ability to suddenly be pointing to b plus 1 over 2 children out of nowhere. So that's why the root has a different minimum rule than the other nodes do, because this root didn't necessarily exist to start with. When it first pops into existence, there's only two things for it to point to. And so that's kind of a recap of insert. Most of that we had done in the last lecture. The rest of it now you're seeing for the first time now. And so that's the insert procedure. Now for remove, it's going to start out in a very similar manner. When we do a remove, we're going to say, well, first you find the location for the leaf you're looking for. Assuming it's there, then you're going to delete it and remove an index. So we'll say, for remove, you will find your leaf, and of course, if you don't find your value in a leaf, it's an unsuccessful search and you're done already. There's nothing to remove. You remove leaf. Remove an index from the parent, and now, as before, you check the parent. So we can put up an example of this as well. That's how things started out. And let's go ahead and put up an example of this. We can have here, there's my black marker. Couldn't find my marker. Let's say we have here an example of, say, whoops, let me put this on a piece of paper. Have here 26 again. This side will have, say, 40, and we'll have here 30. This will be 29, and this will be 32. And we'll have here 50, 45, and 49. And on this side, we will have this be 13. Here we will have 8. Here we will have 19 and 21. So we'll have here 18, 20, and 22. And then here we'll have 8 and 10. And so we'll have here 6, 7, 6, 9, and 11. And I think I've got everything okay there. 6, 8, 9, 10, 11, 13, 18, 19, 20, 21, 22, 26. Yeah, it seems to be legal. If I've made some hideous mistake, I'll have to come back and retape the lecture. But I think everything's okay. I'm just making this up. Oh, there isn't. Okay, this should be 59. There we go. 45, 50, 59. Now everything's okay. So, that said, what we're going to do first is delete the value 11. And so I can say, well, if I want to delete 11, I first have to search for it, and I say 11 is less than 26, it's less than 13, and it's greater than 10, and so that brings me to that node, and then I say I delete 11, and I also delete an index from the parent. And we only have one choice of index to get rid of here. I can get rid of only 10 because that's the only one option I have. If I was instead getting rid of 9, I could have gotten rid of 8 or 10 because I could have resulted then in this node. If I got rid of 10, I would have 6 and 11. Or if I had gotten rid of 8, I would have had this node. And both of those are perfectly legal B-tree nodes because in both cases, the left is less than or equal to the index and the right is greater than the index. That's if I was getting rid of 9. And so that can be a situation then where we have an option. We would just have one coded in. We could say always pick the left index unless you're the very first node, in which case pick the right index. Because no matter which one we pick, we have a special case. If I say always pick the index to your left, then if you're removing the first node, there is no index to the left. And if I say always pick the index to your right, if I'm removing the last node like I am here, there is no index to your right. So either way, you'll need to code a special case. You just enforce code and you say, if I'm anything but the first node, I delete the one, I use the one to my left. So in the case of here, you would get rid of the left. In the case of 9, you get rid of the one you're left and you're left with here. And then you say, if I am the first node, then I'll get rid of the index to my right, because that's the only index I have. It doesn't really matter which one you get rid of. The point is that the tree remains legal. And so deleting the first node requires you get rid of the index to its right. Deleting the last node the last child in that node means get rid of the one to the left. And any of the center ones And if you had like 20 children, then children 2 through 19 would be center ones. You'll have a choice of 2 indices, and however you happen to code it, that would be the index that gets deleted. Anyway, the point here is we found the leaf, we removed the leaf, and we removed an index from the parent, and those were exactly our instructions here. And so now that we checked the parent, the first thing we need to worry about here is what if we have, this is, again, we're down to cases here. Case 1 is no underflow, because now we're removing, we're concerned about dropping below the minimum. And if there's no underflow, we can stop. And that's what we can do here. There's no underflow in this situation, and the reason there's no underflow is because what we're left with is this node in this case. I'll just sort of draw it down here. We're left with this node with 8 as an index because we got rid of 10, and we have 6 and 9 as leaves because we got rid of 11. But that's perfectly okay. We're allowed to have between 2 and 3 children, and so 13 would be pointing to this, and there's no underflow there. There's not a problem. So therefore, we can stop. And that's the easiest case. There will be 3 cases for insert. There are only 2 for remove. That's the easiest case for remove, is when you delete and there's no underflow, and so you stop. And so I'm actually going to go ahead and erase that on the original picture. And now you've got that case here. So let me darken a few things in now. Here we've got 8. And there's our node. That hopefully is straightforward enough. We're left then with a node with 2 children and 1 index. So now the second case, let's go ahead and delete 6. And again, the rule is find the leaf, so we find 6, delete the leaf, and delete an index from the parent, leaving us with 13 pointing to, whoops, not 19. 13 pointing to that tree structure. So when we get rid of 6 and the index, we're left with this. 1 child, 0 indices. 1 child, which is 9, no indices. That's still correct for that rule 4 ratio, where we say the number of indices has to be 1 less than the number of children. So even though we're down to 0 indices, that's okay. The point is we want to get rid of a child and an index from its parent. That's very, very important, because we always want to have whatever we have here, we have 1 less inside the node. And even if it's 0, the point is to have 1 less. That's what's important. So don't get scared off by that we have no indices there. We're going to fix that in a minute. But for now, it's very important that we continue to have 1 less here, 1 less indices than children. So now what do we do? And we have 2 possibilities. One for sure that we're going to use in this case, but in general, we have an underflow, and that's the important thing here. We have an underflow, and so there we are below the minimum number of children. We have only 1 child, and we're supposed to have 2. And there are 2 different ways to deal with underflow. The case that we're concerned with here, underflow, and the other condition is you can steal from an immediate sibling. If so, if you can do that, then you steal and you stop. So there's 3 important ideas there. Firstly, the idea of stealing, and secondly, the idea of immediate, and thirdly, the idea of sibling. The first is the operation we're actually going to do, and I'm going to describe that in a moment. The second and third word, their immediate sibling, are very important. Inevitably, we stress this over and over again, and there's always someone in the class that gets it wrong anyway. So I'm telling you, don't be the person that makes that mistake. It's best for you if you remember you can only steal from an immediate sibling. What we're going to do here, let me at least give you an idea before I go through the operation. What we're going to do is to say this is an immediate sibling. Remember, siblings are 2 nodes that have the same parent. These 2 nodes have the same parent. And immediate is going to be right next to it. So these 2 nodes are right next to each other, as opposed to if 13 had another child over here somewhere, those would not be immediate siblings. I'm going to go over that first before I finish the operation. But what we're essentially going to do here is say I'm stealing a child from 18, or stealing a child from my immediate sibling, which will put 9 and 18 here and have 20 and 22 in another node. And we'll fix that in a moment. But first I want to discuss the idea of immediate siblings and why that term is so important. Basically, the problem is going to be we need to repair index values as well as nodes. So if I had a situation here where I had some root node and then some very, very large subtree, that one of the very last nodes here underflowed. And so we had here a leaf. And so, these are all leaves as well. And then I had some other very large subtree. And I had, this was the node. Basically, I'm just saying I'm not going to bother showing all the details here. Say the value in this leaf is 18, and the value up here is 20, and the value that's here is 22. So the point being, these two are not siblings, because I have this huge, huge long tree that leads down to this node, and the huge, huge tree that eventually this is a node for. I can't steal the node 22 over to the node 18. Yes, this node here is underflowing. It has only one child, 18. I cannot steal 22 and move it over here. They're right next to each other if you read across one by one. But they are not siblings. And because they're not siblings, if I'm going to move 22 over to that node, now I will have 18 and 22 in this node, and yet I'm supposed to have everything to the left of 20 be less than 20. So either I will now have 18 and 22 by stealing 22 over. I'd end up here with two nodes here, and here I'd have 18 and 22. So these two nodes would look like this instead. Whatever these were, it didn't matter, but 18 and 22 would be moved to this side. Either I'm going to be content with an illegal B tree, which is silly, we have rules for a reason, where you'd have here 18 and 22, and yet they're both presumably less than 20, which of course is not the case. Or I have to do the correct thing and fix this tree by changing this index somehow. Which means by stealing across, I'd have to now search upward and fix all sorts of indices that could be messed up on both sides. That's going to be a very expensive operation, and we'd rather not do that. So the idea here is we're only going to steal from a sibling because when we steal from a sibling, as we're going to do in this case, it's easy to fix the indices. We've already, presumably, as we've traversed down the B tree, we've read the parent into memory. So I've got here this node that I'm messing with. Previously, I just saw the parent, and I'm going to now look at this node. And I'll just sort of go, basically I'm going to shift some indices around between those three nodes. But that's not a problem. But if I start having to shift not just the parent of this node, or the parent of this one, but other nodes up this path and up this path up to the root, that is a serious problem. It's going to be too computationally expensive. So if the two nodes share the same parent, we're just messing with these two nodes and their parent. The node we're stealing to, the node we're stealing from, and their parent. But if the nodes are not siblings, if the node we're stealing to and the node we're stealing from are not siblings, then it's not just each node's parent that is involved, but eventually at some point upwards where these two nodes are eventually connected, which could be a few levels up till we reach the root. And that is not a preferable thing to have happen. So when we steal, we have to be stealing from a sibling. Now it also has to be an immediate sibling, though that's not quite as serious. This is a very serious problem. If we're stealing from something you might look at and say, well, why can't, let's say I have here a situation like this, where I have 5 children, and this one underflows, but I have enough children here, and enough children here, or 3 children here, and maybe this one I have 4 children from. And you might say, well, why can't I steal this child over to here, and then take that child over to here, and then take that child over to here, and then take that child over to here? This node is going to gain this child and lose this one, so it's still at 3. This child is going to gain this one and lose this one, so it's still at 3. That child will gain this one, lose this one, so it's still at 3. This child gains this one, so then it's at 2, and it would be okay. Actually, if we have an order 5 B tree, then it would underflow and it would drop below 3. So I guess this is what I'm saying. You have 2 here, so if it's an order 5 tree, there's an underflow. These are all exactly at 3, which would be the minimum for an order 5 tree, and that's at 4, which is not quite the minimum for an order 5 tree. So we'd say, well, why can't I just take this and move it here, 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 and now I can correct this. And that's true, except in order to do that, we had to read all those nodes. And remember, the whole point of a B tree was I don't want to read too many nodes because they're all scattered about a disk. So while it's worth it to me to say, okay, I've come from the parent, I'm now at this child, and this child now underflows, it's worth it to me to look at one node and try and steal its value. But if this node is at the minimal number as it is here, and I would have to then, if I stole from there, now correct it by stealing from what's next to it, and correct that by stealing what's next to it. And we'd sort of do this chaining of steals all the way from the far right child of a node to the far left child of a node. We're having to read in all the children of a node. And for an order, say, 199 tree, this gets ridiculous. If I had here a far left child, a far right child, and total here I had 199 children, I'm going to have to read all 199 children into memory from the disk and then move a child from here to here, and 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 so on to finally correct that underflow. And that's a huge, massive expense we don't want to take. So we don't chain removals through a whole string of nodes like that. We basically say, I'll look at the node right next to me. And if that node is something I can steal from, great. I'll steal from it as we're about to show in the operation we'll discuss, and everything's fine. But if it's not an immediate sibling, if it's a sibling, but the immediate sibling means right next to it, this node, the first child and the third child are not immediate siblings. The first and the fourth are not immediate siblings. The first and the fifth are not immediate siblings. These two are immediate siblings. These two are, and these two are. And that's it. So yes, a middle node has two immediate siblings. This has both of these as immediate siblings. And you could read both of them into memory and say, can I steal from either one of these? And if you couldn't steal, then we'd hit a case 3 in the remove algorithm, which we haven't talked about yet. And if you could steal from one of them, then you steal from either one. Whichever one you want to steal from works just fine. But that would be the idea here, is if you can steal from an immediate sibling, you will, because that will stop the operation. If you can't steal from an immediate sibling, then the eventual thing we're going to do to correct that will result in a continue where we look up and go to the parent. When we don't want to continue and check the parent if we don't have to. So stealing will stop the operation right there, just like not underflowing to begin with will stop the operation right there. So we will always prefer to steal if we can, but only from an immediate sibling, not from some other sibling, and certainly not from something that's not a sibling at all. It's important to keep that in mind. But in this case, we have an immediate sibling. This is the same parent, 13, so it is a sibling, and it's the sibling right next to you, and we can steal from that. If I was to take a node from here, there would be no underflow. Because you can say to yourself, well, technically we can steal from anything, and yeah, we could. When we say we can steal from a sibling, what we mean is you can steal without underflowing, that it's legal to steal. And it is here because if I took an 18 away, I still have 2 children left. Where if I didn't have that, if I only had 20 and 22, I can't steal from that node. We wouldn't have 19 either. So if I have just 20, 21, and 22, I can't steal from that node because it would underflow that node. So that's what we mean by you can steal. We mean you can steal without violating, without making the node itself illegal. And so that's what we will do. We'll say we have this node, and then we have this situation here where we have 19 and 21. And here we have 18, and I have 20 and 22. And the result here will be, I will have here 9 and 18. We're going to worry about indices in a moment. And we'll have here 20 and 22. So essentially what we're doing is we're saying this node should point to 18 and forget that connection. And that now equalizes the number of children. We were able to, this was a child short, we were able to give it a child, and this could afford to lose one, and so it did. Question is, how do we fix these indices? Because now what I'll have here is I've got 2 children, but I still have no index value. And here I've got 2 children and 2 index values. And your first impulse might be to say, well, I'll just move 19 over, and now I'll have 19 there. Now I have 20 21 and 22, and 9, 19, and 18. But that doesn't work. We can't just say, well, I've got an extra index here and I'm short here, move 19 over. We can't do that because clearly 18 here is less than 19. 18 used to be to the left of 19. Moving 18 over and then moving 19 to the left of 18 is definitely going to be a violation because you have to be greater than if you're to its right. And so saying this thing that I am less than should not suddenly become the index to my left. That doesn't work. We don't want to do that. We don't want to just move 19 over. But we're still left with a problem then in that I need an index here and I have too many here. And the answer is to make use of the parent. What I will do in this case, and now I'm going to start erasing the rest of this stuff, is I've got here (9) and 18 as children of this node, and 20 and 22 as children of that node. What I will do is notice that 13 would be a perfectly reasonable index for that node, because we can say here, well, 18 used to be to the right of 13, and 9 was to the left of 13. And so 13 could move down and become an index in that node. And now this node's okay, but the root is short on an index. But that's okay because 19 can move up. 19 used to be between 18 and 20. It still could be. So we'll move 19 up to go into that node. That is, the way we do a steal is we'll pull the child over from the immediate sibling to the node that's underflowing. And then we do an index swap, where the node that was stolen from sends an index to the parent, and the parent sends a different index down into the child. And so the end result is the previously underflowing child gains an index, and it has gained a child, so we're all set there. The parent lost an index, but then gained an index, so it breaks even completely. And then what was stolen from, it lost a child, 18 in this case, but it also loses an index, 19, because that moves up into the parent. The end result being that this is how the tree looks when we're all done. We have 19 up here. We have 21, 20, and 22 down here, and 13 down there with 19 and 18 as children. And so we're all set there. And that's case 2, a stealing case. Now, case 3 is going to be one where you can't steal. And so that would be the case, for example, if I deleted 22. If I deleted 22, well, I look at the immediate siblings, and the question is, how many immediate siblings do I have? I have exactly 1, the node with 13 there. So in other words, the 21 now, I have to get rid of the index as well. So I get rid of 22, and I get rid of 21 as an index. And this node's immediate sibling is this one. Remember, these two are not immediate siblings because they do not share a parent. They have a common ancestor, the root, but it's not their parent. They have 30 has 40 as a parent. This now empty node has 19 as a parent. So the only sibling I look at is this one, and it does not have enough children that I can steal from it without underflowing. So that means I must be at case 3, because my first 2 cases have not been something I can use yet. What I have here is I underflow, so it's not case 1, but I can't steal from an immediate sibling, so it's not case 2, and therefore 3, we combine. Actually, I should do the condition here. The condition here is underflow, but can't steal from an immediate sibling. So therefore, you will combine with your immediate sibling instead. Once you combine with the immediate sibling, then parent loses a child and an index, and therefore you will check the parent. And that means this is a continue case, not a stop case. So just as you would when you split in the insert algorithm, you would then check the parent because it gained a child and an index. Likewise here, because you are losing, the parent will lose the child index, and we'll explain why in a moment. You then have to check the parent to make sure it doesn't underflow, and therefore you continue. And so the idea of combining here, paste this stuff down here. The idea of combining is going to be that, well, we've gotten rid of 22 and we've gotten rid of the index 21 that is in that node. And so I say that this node, well, I can't steal from there, and so the only possibility is to combine. I will take this node and this node, and I combine them to have all the children in one node and all the indices in one node. And so we'll have here 13 as an index and 9, 18, and 20 as children. And we'll always be missing an index there between the rightmost child of the left node and the leftmost child of the right node. We'll have an index there that's missing that we need to fill in. The reason being, we have one fewer indices than children here and one fewer indices than children here. So when you combine them, you'll have two fewer indices than children. If this is, C children and C minus 1 indices and D children and D minus 1 indices, you have C plus D children and C plus D minus 2 data. And I may as well write that down. C minus 1 and C, D minus 1 and D. We have a total of C plus D children, C plus D minus 2 indices. So that is, after we do a combine, we'll be short one index always, and it'll be the place it should go will be between the rightmost of the left child and the leftmost of the right child. But that's the idea of a combine. We're actually going to merge two nodes together. And so if we do that up here, what's going to happen is that 19 will lose a child. And so let me kind of erase this whole big glob, which is increasingly becoming a glob. I'll definitely have to have Charles make slides for this, rather than just reading it off the video, or having you read it off the video, because it's probably getting harder to read exactly. What we have here is that we had here 19, and now this is collapsed into two children that 19 had have collapsed into one child. And we have two problems here. Firstly, we have a bad data to child calculation here. We have 3 children but only 1 data, and we're supposed to have 2 data, or 2 indices rather. And here we have 1 child. The 2 children have combined into 1, so we've lost a child, but we still have the same number of indices. So we have 1 child and 1 index. And so if the parent has 1 too many indices and the child has 1 too few, the solution is obvious. Take the parent's index and move it down to the child instead, so it won't be in the parent. Now the parent has 1 child and 0 indices, and the child has 3 children and 2 indices, and everything's okay. Except, of course, the parent is underflowing, but we'll fix that in a moment. So that's case 3. Case 3 is you take the node which was previously this one, it's underflowing. Since it's underflowing, and since we can't steal from its immediate sibling, you combine it with its immediate sibling instead to give a combined node. And after you combine it with its immediate sibling, the parent then has now lost a child because you had 2 children, and now you have just 1. So the parent has lost a child. You also will have the parent lose an index. And the index the parent loses will fill in the missing index spot in the combined child. So you'll combine your node, your underflowing node, with an immediate sibling, and then you'll be short an index. You'll steal that index from the parent. And that will then finish off this case. So now this node is perfectly legal. 3 children, 2 indices were okay. But now, because the parent has lost a child and an index, it might potentially underflow. We go up there and check the parent. And so that's why we set it to continue case. If you underflow but you can't steal from your immediate sibling, you combine with your immediate sibling, then you take an index from the parent. So the parent loses a child and an index, and so you have to continue by checking the parent. So now we note here what's going on. What's going on here is that the parent is underflowing, so we had a case 3 on this level. Now when we move up, we have another case 3. If I had another index here and another child, then we would just say the parent doesn't underflow. But the parent maybe formerly had 3 children and 2 indices. Now with the combining and the losing of an index, it might have 2 children and 1 index left over, and that would be a no underflow. We don't have that, but we could have had that, where the parent had originally 3 children and 2 indices. Now it would have 2 children and 1 index, and so there would be a no underflow. We'd have case 3 on this level, but case 1 up here, and we'd stop. A second possibility would be, what if its immediate sibling had enough children? Namely, what if we had here, say, 90 and then some subtree here? The immediate sibling of this node is this one. And so it would be possible then, if we had 3 children on this node, to say, I'm going to steal one from my immediate sibling, this entire subtree would move over, and then we'd move 26 down here and 40 up there. If we had some third child on this side, I could steal 30 over and then shift up 40 and shift down 26 to correct the situation. That would be if I had a case 3 here, and then fix this, I have a case 2. So notice when we say we're stealing a sibling or stealing a child from our immediate sibling, we don't just mean we're stealing a leaf. We could be stealing an entire subtree, because here, the level I'm on and the level my immediate sibling is on, they are not the bottom level of internal nodes. The bottom level of internal nodes, when you steal, you're just stealing a leaf. When you start moving up any higher, the children are entire subtrees, and there's no problem with that. So here, what we would have done is stolen an entire subtree. And then things would have been fixed, because I would have had here 2 children with 26 as the index between them. Here I would have had 2 children with 90 as the index between them, and 40 up in the root, and that would be okay. So if that had been my situation, if I had this child, then I would have done a case 3, and then up here to fix this underflowing parent, I could have stolen, and that would have fixed things. But that wasn't my real situation here. I couldn't do a case 1 or a case 2. Carefully delete here. I didn't have this. What I had was a case 3. My node underflows, and its immediate sibling would underflow if I stole from it. This is a huge mess. You'll definitely have slides, which, of course, while I'm talking, you can see these slides. No, you can't actually, because they're not going to be done right away. I'm going to post this up in about half an hour. Anyway, I will definitely have Charles. I was going to anyway, but definitely I'll have probably Charles. I'll have him do this one first, so that you can see the slides here, because this is increasingly becoming a mess. I don't know how it'll show up in video, but it looks like kind of a mess with me looking at it. So I'll have Charles make the slides for this one first. Anyway, the idea here is then that this underflows, and we can't steal from our immediate sibling, so we need to do a combine. That is, we're going to combine these 2 nodes into one node with this is child 1, this is child 2, and this is child 3. And I'm going to go ahead and just rewrite that node, rewrite that diagram completely, and that will then look like this. This was child 1, 13 and 19, with 9, 18, and 20 as nodes. This was child 2, and this was child 3. And so you had here nothing from that node, and from this node you had 40. And so when you combine these, those are your 3 children. We had 40 from this node, nothing from there, and that last thing I had up there. And so there's your combining. And so the root 26 used to have 2 children, now it loses a child. And so you've got 1 child of the roots, and you've got here an index, or a missing index. And so we said we always take an index from the parent and bring it down to the child. So that's the result of that case 3. we had a case 3 at this node, and so we combine it with its immediate sibling, and we get to this point here, where now we have 3 children, we have 2 indices, and now we move up and check the parent. We continue again. So there was a case 3 here, then there was a case 3 here, and now we're moving up to check the parent. And if there was no underflow there, we'd be fine. If we had 3 children of the root, now we're down to 2 with 1 index, we'd be okay. But here we have underflow, and so the last thing to worry about then is this is a root special case. This is our previous remove algorithm, and we need to add one more piece down here, which is the special case of root underflow. And we delete the root. Its one child is the new root. So it's not very hard to deal with, but that's how it works. Because the root is allowed to have as few as 2 children, we will not consider the root as underflowing until it's down to just 1 child, regardless of the order of the B tree. The root is allowed to have 2 children. That was the minimum that it was allowed to have. So if the root is underflowing, you know it has 1 child. And that's the situation here. The root has only 1 child. So since the root has only 1 child, we say this is the new root and delete this entirely. And yes, it fixes the tree, but it's appealing from a conceptual standpoint as well, because the point of these index nodes is to help direct your search to a certain subtree. When I hit this node, I say, depending on what range you're looking for, what number you're looking for, what range it falls into, you'll either go to this subtree or this one or this one. If you keep the root, even though it has only 1 child, what we're saying is, when I hit that root, no matter what you're looking for, jump to the node 2640. We're saying no matter what we're looking for, we read in the root first, and then no matter what we're looking for, we jump here. Well, then we've wasted a disk read. Why read this meaningless node? If this node always tells you to go here, then why not just jump here from the start? And that's kind of what we're doing by deleting this node. We're saying instead of jumping from our root pointer to here and then to here, we're instead just going to jump right to here and say, you know, this root isn't telling us anything useful anymore. It's saying always go to this node. So let's just go there directly and get rid of this wasted node, because it's not helping us make a choice. It's just telling us, hey, pass on through. It's not telling us go to here or here. There's no comparison to be made. It's just a useless node. So conceptually as well, in terms, you can say practically, obviously it fixes the tree, but there's conceptual reason that has appeal as well. The idea that it's no longer helping us make a choice when there's only 1 child, so why keep it? And so then that would be how we'd fix that situation. So way back, when we finally, in the example we had done, we had deleted here 22, leaving this node with 1 child and 0 indices. We combined to form this node, and then we pulled 19 down, giving us here. Pulling 19 down and combining left this node with 1 fewer child and 1 fewer index. And so we combined this with its immediate sibling and pulled down 26 to give us this node. And then the root underflow, we got rid of the root, and that was it. And that's the remove algorithm. You'll notice the remove, the only time the tree ever drops a level in height is when we have the remove special case. Just as with insert, the only time the tree ever gains a level in height is when we have the insert special case. When the root splits and we create a new root, the tree gains a level in height. When the root underflows and we get rid of it, the tree drops a level in height. Other than hitting those 2 special cases, all that's going to happen is we'll grow or shrink from a sort of a horizontal standpoint. The tree never increases or decreases vertically until we hit the root special cases of insert or remove. And there's not much more to say. You now know how to search on a B tree, you know how to insert, and you know how to remove. And you know how to, why B trees would be used, where their usefulness would be. The only other last thing to mention is a really small trivial detail, which is that you have 2 sort of very small cases of B trees, sort of I don't want to say derivative cases, that's not the right word, it's escaping me at the moment, but the case of a 0-child B tree or a 1-child B tree. These are cases where the rules don't really apply because these are just so small as to be almost a meaningless B tree. When you have a null B tree, you're pointing to a null pointer with if this is your root pointer. And then when you insert for the first time, you're pointing to a leaf, your root pointer points to a leaf, and there you go. And then when you insert a second time, let's say we're inserting 10, well, now you will convert this to you have 10 as a second leaf, so you need an internal node between them. And now the rules apply from this point on. This B tree follows all of the rules we looked at already, and any further insertions we do will follow those rules. Likewise, as you start removing, down to the point where you have only 2 leaves, the rules still apply. When I delete, say, 10, and an index, everything collapses down to here, and now at this point we have just 1 leaf, and then if you get rid of that, we're down to null. And so we sort of have the idea of a pointer to null or a pointer to 1 leaf being, the 0 elements or 1 element being sort of special cases that are degenerate. That's the word I was looking for earlier. Degenerate cases. It's such a small tree that it's not even large enough to obey the rules in any particular way. We just say these are special cases. When you have no elements, there's a degenerate case. When you have 1 element, there's a degenerate case. And then once you have 2 or more elements, then this looks like a B tree and you follow the rules. And that's about it. That's B trees. Adam's section, I believe Adam already taped a few days ago the B tree lecture, her B tree section, so you're able to now look at this and look at those. And again, I do apologize for the delay. I'll be taping more of these over the weekend and getting caught up. But at least now we're only a week behind. I'm very sorry that it's taken me so long all the time to tape these. But anyway, now you've got B trees as well. In class right now, if you want to be looking at the book, what we've been talking about is skip lists. And we're starting hashing at this point. And I will record these skip list and hashing lectures over the weekend. On Monday, Adam's going to record a skip list section. And the week after that, he'll record a hashing section. So, but the lecture's now current with all the sections that are online. And I'll have skip lists up, posted in lecture format before Adam tapes his skip list lecture. And I guess that's it. That's B trees. By all means, as always, if you have questions, ask. And I'm going to post these up as lectures right now, and then we'll get slides attached ASAP. And that's it. Lecture 22 will be on, it'll be starting to do with sets and a little bit on unordered lists, and then 23 and 24 will be skip lists. I will see you next time. Take care.